Okay, we're going to take another look at our Boolean laws that we just covered. But now we're going to look at them from a circuit point of view. We're going to have a power source, and we're going to put in a couple of switches here. And then we're going to see if we can get our light bulb to light up, basically. So we're talking here about the switching of these. We're first going to take a look at our Boolean laws that were derived from the AND gate. And previously we said that A and a low input was always going to be a low input. Let's look at that with our switches. And we're going to be putting them in series when we're talking about the AND gates. So let's, filling in that rest of that circuit, we're going to have a switch that can be open or closed. It's a digital system. It can be open or closed, and then in this case we're going to have a second switch that's always open, because this one here is always a 0. It's always not connected. So really it doesn't matter in the circuit if we hook this to a battery and a light bulb. Our light bulb is never going to light because this switch is always open. If we open A or closed A, it makes no difference. We will not get a complete circuit. So that's maybe a way to make these Boolean laws make a little more sense. So now let's look at the second case where we're just looking at the switching portion again. We have switch A, and then we have a second switch that's always closed, always connected. So now what we're saying with this second Boolean law is A and a high, or always conducting, is equal to A. And we see that that's true. If A is in a 0 or open state, the light bulb is not going to light. If A is in a closed state, we are going to have current flow and the light bulb will light. So we can see that the output, is this bulb going to light, is completely dependent on the state of A. Is it open or closed? And that's where we got that from. That's where we got the answer from. Let's look at the third case where we have a couple of switches again. We have switch A, and we have another switch, and we're going to call this not A. So if A is open, then not A is going to have to do the opposite, and not A will have to close. If A is closed, not A will have to do the opposite, and A will have to open. So in no case will the light bulb ever light up. So once again, we have a state of a low state. We're never going to get a high output out of that. Now let's look at the last case of a switch A and another switch that does exactly the same thing as A. So there's whatever this A is going to do, that A is going to do the same thing. And here we can see that the output is going to be dependent on what the input is. Again, if both of the A's are low, the light bulb's never going to light. It's going to be low. If this A closes, that A will also close, and the light bulb will light, and we will get a high. So the output is completely dependent upon A. Again, so let's look at our other Boolean laws, the ones that we derived from the OR gate. And again, once again, we're going to use the scenario of the circuit, and we're going to put a couple of switches in there and see if we can prove these Boolean laws to be true. In this case, I'm going to draw this just a little bit bigger. So it won't disappear on me every time This case, we're going to take an example of a parallel circuit to make it work. So I'm going to put in two switches again. I'm going to put in switch A up here. And I'm going to put in a second switch down below. And in the first case, A or an open circuit, which this one's always just going to be open. The output, as we can see, is dependent on what input A is. we will never get the light bulb to light based upon this open circuit, which will always remain open. And so therefore, we will get current through this branch only if A is closed. So if A becomes 1, our light bulb will light, we'll get a high output. If A is 0, the light bulb won't light. So we're completely dependent on the state of this A as to what the output is. Take a look at our second case of, here's our variable. I'm going to draw this a little bit better. Here's a case of our A switch that could be opened or closed, and we're going to put it in parallel with a switch that is always closed. And we can see from our Boolean laws that it doesn't matter what the state of A is, the light bulb's always going to light because the current always has a path. It's always going to go this way anyway. Doesn't matter if you open this switch or close this switch. We got a high output, as we can see from the second one. Let's take a look at the third one, where we're going to just replace the bottom switch again. And this time we're going to replace it with a switch called not A. So if this one opens, this one has to close. If this one closes, this one has to open. And so you can see that in every case, and always, our light bulb will be on because current will either flow through this path or this path, and the light bulb will light. So there's our third rule down, our Boolean law, that A or not A is always going to result in a high output. Let's look at the fourth one, where we have whatever the top switch is going to do, the bottom switch has to do the same thing. So if A is open, both of these will then be open and no light bulb. Or light bulb won't light. If one is closed, the other closes, and the light bulb will light. So the output A is completely dependent on the state of the input A. So this is where we get this law from. A or A is high, then, or A, whatever state it is, the output will match that.